speaker, Anesh Subramanian. His research interests are mainly in climate processes, global and regional weather and climate prediction, and coupled ocean atmosphere data simulation. He's a climate scientist who studies the predictability of global weather systems, such as atmospheric rivers on medium range to sub-seasonal timescales and oceanic influence on prediction in these timescales using both computational models and also observational analysis. He is also focused on improved understanding of the physics process of their representation in computer models for helping improve the predictions. Sub-seasonal to seasonal prediction is a key area of research highlighted in the Weather Research and Forecasting Innovation Act of 2016. He received his PhD in 2020 from the Scripps Institution of Oceanography and completed a postdoctoral appointment in CO from 2020 to 2014. He then went on to become a postdoctoral research scientist and lecturer in the physics department of the University of Oxford from 2014 to 2017. During his term as a postdoctoral research scientist in the University of Oxford, he has studied advanced weather modeling techniques and their impacts on the predictability of El Niño Southern Oscillation, the Maiden-Julian Oscillation, tropical cyclones, and atmospheric rivers. His skills in weather prediction and expertise in sub-seasonal to seasonal prediction is key to pursuing and achieving the current challenge in extending weather forecasting. He then joined the Center for Western Weather and Water Extremes as a project scientist in 2017 to lead efforts on sub-seasonal prediction and data simulation to help improve Western US extreme weather prediction. He then joined the Atmospheric and Oceanic Science Department at the University of Colorado Boulder in 2019 as an assistant professor and continues his research on prediction of our Earth systems from weather to climate timescales, as well improving our understanding of climate process. He's author and co-author of more than 80 different publications. Thank you very much for coming. Thank you.
Thank you. Thank you for the kind introduction and thank you for having me over. I'll be mainly talking about data science-oriented projects that I've been involved with and I'm involved with in the current and future. And a lot of this work that I'll be presenting, especially in the second half of the talk, are led by students and postdocs in my group. And I've listed many of my collaborators as well across NCAR, the European Weather Center, ECMWF, and as well as IHARP, which is the NSF HDR Institute, which was funded in 2020, last year, 2022. It's ongoing. So it'd be great. I've already started having conversations with some of you about collaborations, including through IHARP. So it'd be great to pursue some of those. So this is a broad introduction, not only for my own research, but broadly for the weather and climate community. There's information that can be provided at different time scales for weather and climate prediction. So at really short time scales, minutes to hours, what is provided by the Weather Service are warnings, watches, alerts, where you're essentially trying to get people to a safe location or save life and property of livestock. And as you go further out into longer lead times, from days to weeks and months. That's where the subseasonal to seasonal prediction challenge is. That's a timescale that's really hard to predict currently. Our weather models are able to predict out to a few days with really good accuracy, but going beyond that to a few weeks and months, there's a big challenge, both in terms of predicting El Nino or atmospheric rivers that bring water to the West. There's currently a lack of skill in the models, but there's a wide range of applications in the society that demand information on these timescales: water management, agriculture, recreation, ecosystem, all of that needs information on these timescales, weeks to months, for planning. So that's a challenge where there's a lot of efforts from the NOAA side, from the National Ocean and Atmosphere side, to push our prediction skill into that timescale. And some of my research is focused on that as well. And then the climate timescale, almost everyone should be aware there are challenges in predicting climate, but at those timescales, we are not looking at accurate information, but more what are the different scenarios that will play out if you're on a most extreme warming versus a moderate warming, which scenarios would play out on a climate change timescale. So the kind of information that's provided from our prediction systems varies, as well as the application in the society. Along with the information that's provided, these orange lines that are presented in this figure from the World Meteorological Organization, it is a critical piece for how this information can be used. And that provides uncertainty on the information we provide. So if we say that it's going to rain next week, are we 50% sure about it, 100% sure about it? That uncertainty also plays into how decisions are made based on that information. So some of my work is also related to how do we improve our uncertainty modeling in our weather prediction systems? How do we better represent uncertainty in weather and climate models? So just a quick outline from my talk. I'll be talking about modeling uncertainty in forecast systems, impact of what's known as stochastic parameterization. I'll not go into a lot of detail on any of this. I know the audience is really broad, but I'll touch upon the main key points, and then I'm happy to talk to anyone about the details if need be. And then I'll talk about some of the projects I've been involved with where we use machine learning to both improve forecasts as well as improve uncertainty in our models, so what's known as stochastic parameterization. And then more recently, we've been working on using machine learning to assimilate data or observations. How do we blend observations from the real world into our weather and climate models? So that's something we are exploring. We're also looking at causal discovery, where we try and understand causal links, or how is one region in the climate affecting another region using machine learning techniques or causal inference techniques. And then the last section of the talk will be more on the polar science, so the IHARP, the NSF HDR project, the different ongoing projects related to that, where we use machine learning for polar science-related problems. In terms of connections to Earth Lab, there are many connections. I think we are focused on extreme weather and climate events, which is another priority for Earth Lab. Use of large-scale weather and climate models, Earth data across scales is another connection, as well as using advanced data science techniques, where we use advanced machine learning techniques to address different applications. So data assimilation is one, polar science is another one, where there's a big ongoing effort through this HDR Institute, and causal discovery, where we are trying to understand causal links between our climate systems components. I'll come back to this in the end after I present the results. So this is just a brief tutorial on prediction. Probably many of you are aware of this. What's known as the butterfly effect, where a small change in your initial conditions can lead to large error growths in your prediction. This was highlighted by work by Ed Lawrence. It was discovered in the mathematical literature before Ed Lawrence, but Ed Lawrence was the meteorologist who brought this into the weather prediction realm, where he had a very simple model, a 3-variable model. And the 3 variables, when you solve it mathematically, it looks like a butterfly's wing. It's not really. It's the solutions lie along these attractors. And what he discovered was when you solve this, where you initialize the model and you run it forward, small changes in the initial condition can lead to large error growth. So I'll show an animation in the next slide where what's plotted here is all the possible solutions on a X and Z plane. So two of the 3 variables, you're plotting that and all possible solutions. So in terms of our climate system, you can think of this gray dots as all the possible climate regimes that we can occupy in our climate system. And any given day, you will be somewhere on this. So today's weather could be, let's say, somewhere here. Next week's weather is somewhere here. And then in 2 weeks, your weather is in a different location. So the weather evolves along this climate attractor where your system's climate is on this large scale region. And then any given day, you're somewhere there. So what I did here was to pick one location and pick 50 points around that single location. So you're saying that you're not absolutely certain where today's weather is, you're perturbing it by a little bit. And I do that in 3 different places on this climate attractor. And then I'll start the integration of the model where you're trying to predict where this model goes, which is basically integrating those set of 3 equations numerically. And what you'll see is when you're initializing from here, all the 50 solutions lie close to one another. They don't depart very much from each other. Whereas when you start from a different location of the attractor, initially they are all close to one another, but eventually they can either lie here where your weather would be in one regime, whereas here the weather is in another regime of your system. And when you initialize the model here, you get very different regimes starting, even from close to the initial condition. And this is true even in our real climate system. So these are what are known as ensemble prediction of tropical cyclone trajectories. So tropical cyclones, so Hurricane Haiyan, which occurred in tropical West Pacific. It had a big impact on Philippines, bringing a lot of damage and destruction. This is Hurricane Katrina, which brought a lot of destruction in the Gulf Coast. And this was another hurricane called Nadine, so what's plotted in color here is the probability. So similar to what I did, the weather models, they run 50 different realizations for each scenario. And they measure the probability of one scenario playing out. So if it's blue or purple, then you're at a high probability where all the ensemble members are sticking together. So you have a high chance of that solution playing out. So here, the forecast of this hurricane was really well done by the model. Whereas here for Hurricane Katrina, initially there was a high probability, but then there was a large uncertainty in where it would make landfall on the Gulf Coast. And in the third case, Hurricane Nadine, it could have either gone towards the Spain coast or it could have gone into the tropical Atlantic without much societal damage. So there was a large uncertainty in the solution. So this is what we are trying to capture. How does uncertainty evolve in our forecast, given that the system is a chaotic system, that small perturbations or small changes in our initial conditions can lead to large error growth, both on weather timescales, but also climate timescales. This again plays out. So the sources of uncertainty in our weather models, one is this initial condition uncertainty, which is the butterfly effect, where you don't exactly know what the conditions are today to start your model from today's forecast and run it forward. So that's uncertainty in our initial condition. Another big source of uncertainty is model uncertainty itself. We don't accurately know what all the physical processes are in play in our Earth system. So we need to represent both the physics in the model, so these clouds, radiation, surface fluxes, many different physical processes are parameterized in our climate model. How do we represent their uncertainty? We don't accurately know the physical process, so how do we represent how uncertain we are about these physical processes? So what's done in weather and now in climate modeling centers as well as for the initial condition uncertainty, we sample an ensemble. So we sample multiple realizations of your initial conditions, representing how uncertain we are on the initial condition. And then for the forecast model to represent the uncertainty in our physics parameterization, we add what's known as stochastic parameterization. So we perturb our physics with some stochastic noise, random noise, and the characteristics of the random noise is based on how uncertain we are on the physics process itself. And so this initial condition is fed into the model. The model adds the stochastic noise and it gives us some forecast of the future. And that the goal of this is the uncertainty cloud around the future forecast is hopefully accurate. It captures the uncertainty in our system as we project forward in time. So one common uncertainty, I'll not go into detail of this, one common stochastic parameterization that's used in weather models is all your physics solutions of the wind, for instance, like the U and V wind field in the Earth system, temperature and moisture in the Earth model. You take the tendency at each step and you multiply it with a random noise. So you add a multiplicative random noise term. And this multiplicative random noise term is based on our knowledge of how uncertain our physics parameterizations are. So there's the knowledge of uncertainty that goes into this stochastic parameterization or random perturbations in our weather model. So some work we did for this was to understand the impact of this stochastic physics on what's known as the Madden-Julian oscillation, where if you're not familiar, so have you heard of the Madden-Julian oscillation, the MJO? So the MJO is a large-scale precipitation pattern, so set of clouds that can be like 10,000 kilometers wide. So it's a large wave in the tropical region. So here the blue indicates more rain and then the red is less rain. So it's a wave where you have more rain and then less rain ahead of it. And this propagates from the Indian Ocean into the Pacific Ocean. And it actually goes around the globe, the dynamical signature. And the Madden-Julian oscillation, it has a signature around the globe. It definitely impacts the region around it. So Africa, Southeast Asia, Australia, all of that is directly impacted by the rain from the Madden-Julian oscillation, but it also impacts atmospheric rivers that come into the Western US. It has a direct teleconnection into Western US water. And the timescale of this phenomena, this wave is like 4 weeks to a month. So it lasts to 4 weeks to 3 months, sorry. So it can last 30 to 90 days. And the reason that timescale is really important is once this wave starts going, you are able to predict it pretty well out to 3 weeks. And that plays a big role in terms of prediction on these subseasonal to seasonal timescales. So it acts as a source of predictability on these longer timescales. So if we are able to predict this wave propagating through the tropics, we can predict, like, is there going to be more precipitation in Western US, or is there going to be more precipitation in the tropics? So that's why this is important. I'll not go in depth into this. This is a measure of how good the model is in terms of predicting this Madden-Julian oscillation. The higher the value on the lines, the better the skill is. The red line is where you don't have any stochastic parameterization, so no stochastic physics within the model. The other lines are different configurations of the stochastic physics that I showed you. And what we show here is that whenever you have stochastic physics in the model, the uncertainty in the model, it's able to predict this Madden-Julian oscillation better. So the skill out to like 3 weeks, 20 days is higher when you add this stochastic physics parameterization in your weather prediction model. So that's one study. Another one we did was impact of this stochastic physics on forecasting atmospheric rivers. So for this, we used a slightly different implementation of stochastic physics, where we actually have multiple realizations of a cloud model embedded within a weather model. So you have a global weather model, but you embed a cloud model within each grid cell of the weather model, and you slightly perturb that weather model. So it's called a super parameterization framework of predicting weather. And for this, we looked at predicting an atmospheric river that made landfall in northern UK. It was an extreme atmospheric river that brought the highest precipitation observed in this region, the Cumbria region, northern UK region. It brought a lot of destruction to property, life, and the society there. So we were looking at medium time scale, so 6 to 10 day forecast of this weather event. So the middle panel is the reanalysis. So it's what actually occurred on that day. The color is what's called integrated vapor transport. So that's one way to track atmospheric rivers. So atmospheric rivers, they carry water in the atmosphere from one region to another along this elongated tract. So this year in California and the West Coast, you had a lot of precipitation due to these atmospheric rivers. So this phenomena occurs both in the Pacific as well as the Atlantic. This was an atmospheric river that brought extreme amount of water vapor in the North Atlantic, bringing the precipitation to northern UK. So what's plotted here is, this is the traditional or like the conventional stochastic physics parameterized model predicting this atmospheric river. It had a signature of an atmospheric river where you had this narrow plume of water vapor, but not as strong as the observed atmospheric river. We use this embedded cloud model formulation, and we show that it actually enhances the strength of this forecast. So you see a better prediction of the strength of this atmospheric river out 6 days, like out to 1 week. And it's really hard to predict these events because they are short-lived. They last for a day or so. And being able to predict it 6 days out is a challenge. But adding this kind of embedded cloud model, it's able to keep the water in the atmosphere for longer, which is why it helps to predict these atmospheric river features better in the long term. So now, so those were physics-based approaches to improving prediction of our weather in climate system. Now I'll present results on machine learning approaches that we did. This was work done by a student, Will Chapman, who's now at NCAR, where we used CNNs, so convolutional neural networks, that essentially you feed in some data to it. And when you train the model, you tell what the actual cat image looks like. And you can define a cost function. So a cost function is all the parameters in your neural network are optimized based on your erroneous prediction. So how bad your prediction is, the cost function is higher, and you want to reduce this cost function. So we try and find the optimal value or the lowest value of your cost function where the parameters in your neural network or optimized to predict which image is a cat image based on the training. So we did this not for cats, but for atmospheric river images. So the question was, can we use this to operate on an image data of atmospheric rivers? Because atmospheric rivers or tropical cyclones, they are features in our weather model. They are phenomena that if you look visually, you can say it's an atmospheric river. Right? You have this narrow, long plume of water, similar to a tropical cyclone, that you can see a tropical cyclone in a satellite image and say that it's a tropical cyclone. So the question is, can we use this technique to spatially correct a forecast? So if the forecast is telling us that the atmospheric river is weaker or it's going to make landfall in Seattle versus California, can the machine learning model detect that error and correct it after the forecast is produced by the model? So that's the approach we took. Currently, most of the what's called post-processing, which is processing of forecast model output, is done using single point correction. So you take the value at Seattle, you see if the model is like historically wrong in predicting precipitation in Seattle, and you correct the value of precipitation based on that historical information. This approach is taking a more of a global approach where you look at the entire image, say if the atmospheric river is wrong and correct it. And once this neural network is trained, it's fast to run and implement in the model, because once you have the parameters, it's fast to feed it a forecast image and ask it to correct it. So we did this over the Northeast Pacific and the US West Coast. What's shown here is the improvement in skills. So all the blue colors show that you have a better skill when you apply this machine learning approach to predicting atmospheric rivers. And the red colors indicate that the skill is decreased. So here we take a forecast model output, like 4 days out. You feed that image of like the integrated vapor transport. So the variable that represents atmospheric rivers, you feed that into the neural network. And then the neural network will tell you if the forecast was wrong, how to correct it based on like training, based on historical prediction of atmospheric rivers over this region. So we were able to show that you can actually improve the model much better than traditional methods using this approach, using a machine learning correction approach. And then there's follow-on work. I'll not go in depth into this, but the follow-on, so the previous one was just a deterministic forecast. So you give it one image, it produces one corrected forecast. It does not give you uncertainty around that forecast. So we further developed that to include probabilistic information, to give a probabilistic prediction of the atmospheric river correction. And yeah, so I don't have results from that, but the paper is published where we show that using probabilistic cost function within a CNN framework, you can produce ensemble forecasts. So you can improve probabilistic prediction as well with machine learning. And then, yeah, so the next work I'll present on is, so from now on, it'll be, yeah, just a few slides on each project. So it's an overview of the different ongoing projects. So here we are looking at stochastic parameterization of the simple Lorentz model. So this Lorentz model, it's a further advanced Lorentz model than the Lorentz 63 butterfly model that I showed. Here we have 40 variables around the globe. This is representing circulation on one latitude around the globe. And the goal here was to parameterize the fine scale forcing. So if you think of the climate model, you can think of the solutions of the climate model to be X. And then these small circles can be thought of as the cloud model, the super parameterized cloud model, right? That's much more expensive to run. So those are smaller scale features that impact the larger scale climate. What we want to do is to parameterize this small scale forcing that impacts the large scale. So instead of having to integrate or run a fine resolution model that is computationally expensive, can we represent the impact of these small scale features by parameterizing that component of the model. So using a machine learning approach to parameterize subgrid scale processes. So for this, we used what's known as generative adversarial networks. So the idea is that you have two neural networks that are competing against each other within your machine learning approach. So one of them is called a generator. It creates synthetic samples of your data set. And this synthetic sample is then provided to what's called as a critical network or a critique network that has information about the real true sample or the real data from your model. So it tries to compare and say if the synthetic sample looks as good as the true sample or not. So this is called a generative neural network, where you're essentially training this neural network to produce realistic information. And the way this is done is by competing it against a second neural network. So it's called a generative adversarial network. Adversarial is where these two neural networks are competing against each other to optimize both to produce like a synthetic sample. And then this critique network feeds back to the generator network and makes it better in producing synthetic samples. It keeps telling it this is not a good enough sample. It doesn't look like the truth. Improve your network to generate better samples. So we did this within the Lorentz model, where we feed it in the large scale solution, and we ask it to give us what's the subgrid scale parameterization, what's the forcing from the fine scales. Yeah, so we did many different configurations of this. I'll not go in depth into this. The key highlights from this is that, yeah, so for many different samples, we looked at the weather error. So this RMS is root mean square error in your weather prediction within the Lorentz system. And then the Hellinger distance is the climate timescale measure. It measures how good your model is on a climate timescale. So it's looking at a long-term solution and the probability distribution on the long-term solution. And we show that there are configurations of this GANs, like the generative adversarial networks, that do well both in the weather timescale. They have a low error as well as a good representation of your climate system too. So you can train generative adversarial networks to produce subgrid scale parameterization that are computationally cheaper, and they do give us a good climate and weather prediction in this idealized framework. So I'll end the part one there, where I showed that physics-based uncertainty and stochastic parameterization both improve Madden-Julian oscillation forecasts as well as extreme events. So I showed an example of atmospheric reverse. We have done this for tropical cyclones as well, showing an improvement in tropical cyclones. And then we have used machine learning approaches that can help weather and climate forecasts as well. In the second half, I'll dive deeper into the polar science projects that are ongoing, which is part of iHeart. But if you have questions on the first part, maybe I can take them now. Yeah.
How many images did you need of the atmospheric rivers to train that model?
Yeah, it's a really good question. So we took 15 years of
15 years
of daily data, yeah, which is available now. Like people, there are like 25, 30 years of forecasts from the past.
Okay.
So we took 15 years, trained the network, and then like ran it for the next 10 years or so.
Okay. And how many images was that?
So the number, so it's daily, so 15 into 300, I guess. So
Okay.
45,000 or.
Okay. So it's in the thousands.
Yeah.
I was asking in part because I'm like wondering how the ecology and environmental sciences are gonna attract someone like your attention to the problems that we have. Like, okay, how many images do we need of species and ecosystems?
Yeah, some of these, they do need a large training data set. But then there are other approaches where like you can produce synthetic data. If you have a short time record or shorter data set, you can train like a smaller network to produce like synthetic data that looks like real data.
Yeah.
And then people use that like to augment the data set and train like a bigger network. Yeah.
So I love the work on the Lorenz attractor. The very first, so ESOL was part of a family, and the very first one, that was their logo, because in ecology, sort of in the 70s, they discovered the population dynamics.
Yeah,
sort of
right.
has all the same thing. Now, my question, I guess, is one thing that kind of came out of the ecology work on this population dynamics stuff is that it sort of depended on growth rate.
Yeah.
So if growth rate was really low, things were predictable. You didn't go into chaotic behavior. If growth rates really got high, then you start getting bifurcations and things get unpredictable. And so natural selection is always pushing.
Yeah.
In a case where we don't have natural selection and it can go easily into sort of chaotic behavior, how much does that go into the model, this sort of raw growth rate of sort of the emergence of the property?
Yeah. Let me see if we can switch. Yeah, so what you say about growth rate is also true about the Lorenz attractor space, where it's computed as the Lyapunov exponent, like it's the error growth rate in your system, which is a function of the equations, basically, right? Like these three equations, that's a question in the chat. So they determine like the error growth rate. So for any nonlinear dynamical system, you can compute what's the error growth rate, and it's a function also of where you are on the state space. So similar to that, like I said here, this is predictable because the error growth rate at this location on your attractor is small. So then when you start your model from there and run forward, the error growth rate is smaller compared to if you're in a location here on the attractor, then the error growth rate is much larger. So if you start integrating your model, the error grows at a larger rate. So you have more uncertainty, or it's not unpredictable compared to the first case. So it's very similar to the.
But there's not a selection in this case. It can just like, it can equally go anywhere in the probability space.
Not really. It is governed by the dynamical equation. So that's where the selection would play out, I would say. Like the equations determine how the physics plays out in the system, and that selects where you are going on your trajectory. So you can either go into this lobe or this lobe based on the equations and your initial condition. So that's where the selection plays out in this framework. It's different from the natural selection, but a similar idea, I think, that the dynamics are governed by the equations of your physics system, and that tells you like where you're going the next step, right? You cannot go, like if you start from here at the next time step, you cannot be anywhere on your attractor. You have certain directions that you can go that lies along the trajectory of this attractor.
Yeah. Thanks.
Great. Yeah, great question.
Yeah, thanks.
And then there was one in the chat.
Oh, yeah.
I don't have it up, or I would read it for you.
I think the screen is from that laptop.
Yeah.
It's trying to move my mouse. See my mouse here.
Yes, do you have it open? Do you know what the question? Oh, okay.
There it is.
Yeah, that's a great question, Elsa. So if I understand it right, you're saying, how do you know that the GAN models will be valid for a new location or regime that it has not seen in the training data set? If that's the question, so I think the answer is we don't entirely know. We tried it for the Lorenz model where we gave it a long time series, but not the entire solution of the Lorentz model, and it still was able to do well in the validation period where it had not seen some of the regimes in the past. But for a real climate system, I don't know if it will be able to predict like a climate change scenario. If you're like in 2100 and your tropical cyclones are extremely active, I don't know if GANs will be able to do it. I don't know even if our current climate models will be able to do it. They are constrained by the physics equations that we understand today. So they are able to constrain to that physics. GANs are not necessarily constrained to physics themselves. So that part is free. I would say, we don't know entirely yet, but being able to constrain it with some kind of physics would help. And that's something we're exploring now. There are physics-constrained neural networks. So thanks, Elsa. Hopefully that answered your question. I'm pretty late. I'll quickly run through the second half, and I'm happy to talk to anyone in detail. So the first project I'll present is by Luke Howard, who's a grad student in our group looking at data assimilation and augmenting data assimilation with machine learning. So this is just a quick tutorial on data assimilation. If you have your model that is, so the observations are in the red dot here. Your model prediction is on the orange line, and the truth, let's say, is the green line. You want to push your model towards the truth. The model has errors, but whenever you have observations, you want to correct your model and start the model to run from that new location where you have a better initial condition or a better representation of your system. So Luke has been looking at how do we improve our conventional methods, which are computationally expensive, to assimilate observations. So one of the motivation is we have like terabytes or petabytes of satellite data. One of the satellites is satellite radiance. And the amount of data that goes into our weather prediction model is like 0.01% of the actual observed satellite data. And that's because of the computational expense of getting this into the weather model. So if we can make it computationally cheaper, we can hopefully get it from 0.01% to like 0.1% or 1%. That would be a big win. Because these satellites, they're millions and millions of dollars to put it into space. Data assimilation is not the only application of it. People use the raw satellite data for other information as well. But being able to better leverage this in our models will definitely help. So what we do is not use the real model, because getting there is a process. We start with a simpler model, the Lorentz model that I had shown you before, the same Lorentz 96 model. But then we have examples where we take high resolution observations and low resolution observations within the Lorentz model framework. So this is an idealized experiment. We run the model forward. We call that as our truth. We take observations from that true solution of the model, and then we run the model with an error in the model solution. And we try to assimilate the true observations into this erroneous model integration. So we ran 3 different cases. So the one which most represents our current scenario is we only assimilate sparse observations, like sparse in space, or like sparse in terms of like the density of observations. The ideal case is where we assimilate all observations. This is using a mathematically accurate data assimilation method called the ensemble Kalman filter, where you have an optimization method to optimize the model and observations. And here we use a machine learning augmented method where we assimilate low resolution observations using the Kalman filter and then use machine learning to assimilate high resolution observations into the system. And yeah, one quick result from this is the same, the root mean square error. The lower it is, the better the skill in the model. And here we show that the augmented method, the blue line, is better than the red line, which is the sparse ensemble Kalman filter. So augmenting the conventional data assimilation with machine learning approach to assimilate more data into your system can help improve the forecast in the model. So this is a 10-day forecast with the Lorentz model, and it helps improve the forecast throughout that time period. Then, in the interest of time, I'll skip this, but we use an explainable AI method called SHAP, where you can look at what exactly is the machine learning method training to, what is it detecting in terms of the input features that are most important for correcting the system. And we show that the SHAP values, the explainable AI, it detects that the 2 grid points away from you is the most important data. And that's also relevant to the mathematical equations of the model. So we are able to see that the neural network actually learns some of the dynamics in the equations, even though it doesn't know anything about the equations. Then another project that a student is pursuing, Danny Do, is causal discovery, which is using a method called PCMCI. It's a method where you feed it multiple time series and it tells you which time series is causing an effect in the other time series. So it's a causal discovery method. A more recent approach on this is PCMCI Plus, which previously it was only detecting lag lead relationship if it's affecting in the future or past. An updated algorithm detects contemporaneous causal relationships also. So we are using this to detect impacts on the Asian summer monsoon, which is characterized by the winds in these 2 locations. So you can create an index of the monsoon strength based on the wind difference between these 2 locations. So the stronger this is, the stronger the monsoon is. And what we were looking at is how does pressure field across the tropical basin impact the monsoon strength or monsoon index over that region. So we used the EOF method to subsample or like reduce the dimension of the problem, where we pick the time series from these different EOFs, or different patterns of pressure changes in the tropics. Yeah, I'll not go in depth into the algorithm, but what the student discovered was there was this pressure pattern over the West Pacific, which seemed to have like a 1 to 2 week lagged relationship to the monsoon. And this was not known before. And we have tried to understand what's the physical mechanism behind this causal relationship. And yeah, so she shows that there's actually a wave propagation from this region. And when you have a low or a high pressure in that region, a wave propagates into the monsoon region, and it can affect the strength of the monsoon 1 to 2 weeks ahead of it. So the causal relationship was discovered using this machine learning algorithm. And then we used like a physical analysis of physical diagnostic to actually understand how is it linked, what's the mechanism linking the 2 regions. And then now I'll dive into the polar science projects that are ongoing through IHARP. Devon, who's a postdoc currently in the group, she graduated from here as well. She has been looking at buried lakes. This is like a cool video of a buried lake using a camera that goes below the surface. So when you look from a satellite visual image, you would see that the surface is frozen, but below the ice, you actually have liquid water. And this plays an important role in terms of melting the ice sheet, because when this water drains out, it can melt the ice sheet and cause bigger damage to the ice sheet. So she's been using, or she's working on using machine learning to detect these ice sheets. So you can look at optical satellite images and microwave. So microwave can look below ice, and the water property can change the microwave signature, whereas optical images, they only see the surface. So there you don't see a signature of the lake. The microwave can see the lake. So you can use this to detect these buried lakes and how do they change in different scenarios. So she's been using different classification methods to classify the different features in the microwave versus optical, and you can detect the buried lakes in these features. And then, so the motivation is to study how do these buried lakes change, what are their temporal evolution characteristics. Sorry for running late. I'll finish in a few minutes. And this project is ongoing, where we're trying to understand what are the characteristics of these buried lakes, how do they change in time, how do they impact the ice sheet. Mike McFarren, who's a research scientist at Cities, he's funded through iHarp as well. He has been doing a really cool project where, the motivation is ice sheet ablation. So at the end of the ice sheet, it breaks off and gets into the ocean. And how these lakes, either the surface lakes or the buried lakes, when they melt and they go down or go off the ice sheet, they can break off some part of the ice sheet and put it into the ocean, which speeds the loss of the ice sheet, speeds up the loss of the ice sheet. So he's been working with a company called Earthrise Media through iHarp.
Oh no.
It's back. It's back.
Okay. Where they work with teachers and students in high schools to hand label features and images. So the students get images, satellite images, and then they're asked to describe polygons around features that we are interested in, lakes or rivers on the ice sheet, moraines. So they've been working, they've created a hand labeled data set, which is useful to train machine learning methods. So that's used as a ground truth to train detection algorithms. Another student, Zichi, he has been running a climate model where we run different resolutions of the climate model, where we can run a higher resolution just over Greenland and Arctic region. So here we are not yet using machine learning, but we are looking at what's the impact of resolving higher resolution processes in our climate system on the Greenland ice sheet. And he shows that there are important differences. When you have a higher resolution model, you capture the topography of the ice sheet better, you can capture better atmosphere ice sheet interactions and how the ice sheet evolves. And then, finally, there's a computer science student, Nitin Harilal, who's a student of Claire Montaglioni, who's also working on iHarp. I think, Jennifer knows Claire well, and she's involved with that lab as well. So we have worked on a previous project where Nitin has worked on downscaling. So if you have like a 100-kilometer resolution climate model, how do you generate like 20-kilometer or 10-kilometer information from it using machine learning? The first application he did was for solar energy prediction. This was with Claire, Bree, Matthias Hodge in electrical engineering, and myself, where we were looking at renewable energy applications. How do we generate future high resolution projections over US for solar radiation using machine learning downscaling? And now Nitin is working on downscaling over Greenland. So we have a 30-kilometer resolution reanalysis for like 50 years. And there's like a 2-kilometer resolution regional reanalysis, but only for like 15 years, 15, 20 years. So we want to use machine learning to map from low resolution to high resolution, but extend it back to 50 years. So that's something Nitin is working on in producing a high resolution data set over Greenland. Yeah, so I'll end there. I think, yeah, I would really love to collaborate with Earth Lab. A lot of common interests as well as tools, applications, and teaching. So great, thank you.
Thank you.
Thank you for coming.
Yeah.
Definitely, there are lots of overlapping. Yeah, let's talk more, and I guess everyone here, like, thinking about. Thank you.
I don't see any other questions from folks online. If anyone in the room has questions and you want to stay after, feel free to. But we are right at 12 o'clock, so if anyone needs to run, that's fine too.
Thank you.
Yeah, thank you.